So this is the answer video for exercise 4.3.2. It's about the satiation of Coca-Cola. For the first question, we have to define how the driving force is dependent of the bulk concentrations and the partition coefficient. So we first make a sketch of the droplet, which is going down and has speed v, and there's mass flow going in, because there's CO2 from the air on the outside of the droplet going into the droplet. Well, define the driving force. Because there's mass transfer of CO2 from air to Coca-Cola, there is a driving force. We first have to determine the driving force. Therefore, we first have to look at the partition coefficient, which is the concentration bulk of air divided by the concentration bulk Coca-Cola. So this is then the partition coefficient times the concentration of Coca-Cola, and that is equal to the concentration of the bulk of air. This is when there is an equilibrium. The driving force, therefore, is the concentration of air minus m times concentration of Coca-Cola, because they are not equal to each other, as there is a driving force. So m times Cb of Coca-Cola is a little smaller, and therefore minus m Cb Cola. Then for the second question, we have to determine the Sherwood number for CO2 inside the droplet and CO2 outside the droplets, where there are two ways to determine the Sherwood number, as we have two situations. For the first situation, we have the Sherwood number for in a sphere. The Sherwood number for in a sphere for mass transport, where there is resistance in the sphere itself, we have a standard number. This is 6.6. When it comes to flow around the sphere for the outside of the droplet, there is a formula. This is Sherwood is 2 plus 0.66 times Reynolds to the power of a half times Scandal to the power of 0.33. So we first calculate Reynolds number. This is V times the diameter times the density divided by the viscosity. The density and viscosity are of air. So the dynamic viscosity of air is 1.82 times 10 to the power of minus 5. Then filling in all the numbers. So for the speed, we have 0.01 meters per second times 2.5 times 10 to the minus 3 meters times 1225. And we divide that by 1.82 times 10 to the minus 5. This then equals in 1374 for the Reynolds number. Then for SC, you have to calculate that by taking the kinematic viscosity of water and dividing that by the diffusion coefficient of water. The kinematic viscosity of water, as we assumed it is the same for Coca-Cola, is 10 to the power of minus 6. The diffusion coefficient we have also taken is 1.6 times 10 to the power of minus 9, as we assume Coca-Cola is water. Filling this in the equation, we get 625. Then filling in the Sherwood equation, so 2 plus 0.66 times 1374 to the power of 0.5 times 625 to the power of 0.33, and this equals 206.7, and that is 207. So we have both Sherwood numbers. Then for the third question, we have to calculate the resistance of the air and the resistance of the Coca-Cola. Before this question, we need the Sherwood numbers of the second question. So for the resistance of Coca-Cola, we need the Sherwood number of Coca-Cola times the diffusion coefficient divided by the diameter of the droplets. This is 6.6 as Coca-Cola is the droplets. So the resistance is in the droplet, so it's a 6.6 times 1.6 times 10 to the power of minus 9 divided by 2 times 10 to the power of minus 3. And this equals in 5.28 times 10 to the power of minus 6. The diffusion coefficient is that of water, as Coca-Cola is assumed water. The resistance of air is the Sherwood number of air times the diffusion coefficient of air divided by the diameter of the droplets. This is 625 times 16.4 times 10 to the power of minus 6 divided by 2 times 10 to the power of minus 3. And this equals 5.125. So therefore, we have the resistance of the air and the resistance of Coca-Cola. Now for the fourth question, we had the multiple choice question about what we can say about the resistance. We first have to look at the mass balance, the two mass fluxes. This is of air, this is shown right now, and we also have that of Coca-Cola. Combining these two mass fluxes, we get a total mass transfer flux. This is A times partition coefficient divided by the resistance of cola plus 1 divided by the resistance of air to the power of minus 1 times Cb of air minus m times Cb of cola, which is the driving force. So for the resistance, we look at the total resistance, and this is m divided by the resistance of cola plus 1 divided over the resistance of air. So we need to look at the individual terms. The K of Coca-Cola is really small. This means that M divided by K of cola, the resistance of cola, is really large. As a small number, 1 divided by a small number is a high number. The resistance of air is a larger number, which means that 1 over the resistance of air is a small number. As M divided by the resistance of cola is much larger than 1 divided by the resistance of air, it means that B is the correct answer. So because K of cola is much smaller than the K of the resistance of air, the resistance of air is negligible. And for the fifth question, we have to consider what this means for the total resistance. So from the previous question, we know that 1 over K of the resistance of air is much smaller than M divided by the resistance of cola, which means that the total resistance actually is M divided by the resistance of cola, because 1 over the resistance of air is negligible. As the total resistance only dependent on the resistance of cola, it means that the resistance lays with the Coca-Cola and A is the correct answer.